checking any functionality because we are not giving any input vectors as such. We are only bothered about timing because it's a complete VLSI circuit, very large integrated circuit, which will consist of multiple gates, and checking functionality and timing at a time is not possible when you pick such kind of complex circuit. So that's the reason for VLSI, I mean to say for the gate count, according to the gate count that we are performing under our integrated circuits or ASIC flows, mostly we prefer the static timing analysis. So for the dynamic timing analysis, it checks functionality and timing. It is also called as gate level simulation. So no input vectors are required here. But here the input vectors are required when you go to dynamic timing analysis. So it's faster since it does not involve simulation. Obviously, when it is doing only one process rather than performing two processes at a time, it is obviously faster. Like it is only checking for the timing. So here, if you take in the case of dynamic timing analysis, it is slower because it will consume the time taking simulations. So it is not suitable. It is dynamic timing analysis is not suitable for complex design, and static timing analysis is suitable for complex designs. So why we are going to the static timing analysis is once all the synthesis, the gate level netlist you get from the synthesis is broken into some timing paths, so that the complete circuit at a time we can't run. So the runtime might be more if we inject the complete circuit. So the algorithm is set in such a way in a tool of static timing analysis such that the gate level netlist, whatever you have injected as an input, will be broken into some small timing paths, and each and every timing paths is analyzed according to the constraints that you have given in the SDC file. So here all synthesized designs are broken into the timing paths, and each timing path will have a start point and end point. So any point have to have some point, like any path should have some starting point and ending point. So these are the two types that we have, that is starting point and ending point. So what will be starting points usually will be the input ports of the design, and the ending points will be clock pins of the sequential cell. So if you come to the end points, the data input of the sequential cells and the output ports of the complete design. So in between logic also, the paths are segregated according to this inputs, that is start points and end points. So this and all we'll discuss once we enter into what is STA and everything. So usually there are two types of arcs when you do perform timing analysis. One is cell delay timing arc and the other is net delay timing arcs. So cell delay is nothing but the propagation delay, and specifically cell delay timing arcs are defined by the type of cell delay model that you are using in the technology library. So you guys have observed this library lookup tables, right? So for the cell delay, so the template, like whatever we have checked in the previous session, like 7x7 matrix, according to the input transition and output load, the value of that cell delay is getting picked. So this particular this particular static timing analysis library depends upon the technology library, whatever you are picking, where the type of libraries, that means there are three types of libraries of files again, or delay models again. One is linear delay model and non-linear delay model and current source model. So according to the application that your chip is going to be manufactured, that particular delay tables is getting picked according to the application. So there are some other delay arcs also. One is net timing delay arc, where it is defined by the operating conditions with specify the resistance and capacitance free module to use. So whatever net delay is nothing but the interconnect wire information delay also will be given, as you guys have seen in the cap table. It will also change according to the technology you are implementing. So you can see if this is a complete circuit, how the paths are segregated. So the paths are segregated according to start points and end points. So according to my start points, my paths are from input to clock, clock to clock, and clock to output port. So we'll discuss in deeper in the later slides. And if there are any combo logic, that means there is no connection from input to output in between with the help of sequential cells. So input and output is getting connected only with the combo logic. So in such cases, there will be this information of that combo delay also. So you can see. So how usually STA works is, uh, first it takes in the timing circuits. That means we give a timing circuit, whatever we need to implement. And first the gate level netlist that is synthesized from the synthesis tool, and we add on the timing constraints. Timing constraint is nothing but the SDC file. So first it computes its performance bounds. So once if you write a timing constraint, what is performance is, you just give the frequency like at what your circuit have to function. So first it analyzes or computes what is the complexity of the circuit. How do I analyze the timing? So according to the frequency that you have mentioned in the timing constraints, then it will compare them against its timing constraints. Now you have defined some clock frequency, and under the clock frequency you are defining the delays of the ports, you are defining the delay, I mean to say the transition times of the ports and the loads of the ports. So it will relate that frequency to the remaining constraints, and it will just report or analyze the timing paths, and it will generate the timing report, and it will show us a report if it is passing or it is failing. So this complete execution process is done by an STA tool, and the tool for doing this process of static timing analysis in Cadence is Tempest. So Tempest is the name. I'm putting it in the chat box, you can check it out. So Tempest is the tool here we are using for the implementation process of STA. Now, to perform this static timing analysis, we need the same inputs as such we have given for the synthesis process also. So the extra input we don't give here is, there we have given an RTL file. Now the RTL is converted into gates. So that gate level netlist we are giving as input. The other is the library, same library where whatever we have given for the implementation of synthesis, the gate level netlist that is generated by the synthesis process, and the SDC, same SDC file that you have given for the input a file as a synthesis. So the output you get is timing reports and log files. So what is gate level netlist is, the design is represented by the gates connected in specific manner to achieve the desired functionality. So whatever RTL functionality you have written in the .v file of RTL code, that will be converted into a gate format. And you have already saw this file. So it is the output of synthesis, and it is technology specific. That means whatever gates that are in the .v file have to be mapped to the technology that the design is getting to fabricated. Now if you are synthesizing it in a 45 nanometer library, so while doing the static timing analysis process also, you need to use the same library file, because if you are using different technology library, the gate attributes will be changing, and that will not be mapped to the gate level netlist that you have generated. So you need to use the same technology library file. So gate level netlist is also obtained from the place and route tool, and is used in STA to run post layout timing analysis. So as I told you, STA is having two stages in the implementation process of ASIC. So one is pre-layout STA and the other is post-layout STA. So pre-layout STA is something where we are performing the early analysis if my timing is passing or failing once after synthesis. Now, what is post layout STA is once the complete process of physical design is done, we can write out a gate level netlist after the process of routing, and that one also we can inject it to the static timing analysis tool, and we can perform the timing reports. So here what will be the difference between the pre-layout STA gate level netlist and post-layout STA gate level netlist is, in the pre-layout STA the net information will be estimated. The routes whatever you have given, I mean to say the nets wires whatever you have given in the netlist or you got from the synthesis tool are just the estimated nets or estimated wires. But when you go to the post layout STA once after routing, the gate level netlist will have the actual nets because it's routed. It's actually connected in the Innovus tool. So it will be having the actual net information. So that is the difference when you go to post layout STA. So, and again, this gate level netlist will be in the form of structural Verilog or VHDL format. So the other input is the same Liberty file. So timing library is technology specific and it will consider the functionality and timing information of each and every gate that you have converted using the synthesis process, and you have checked it in the gate level netlist. So as you guys know before also, for the synthesis process, we have used the same Liberty file. So it will comprise of this particular cell. Standard cells are nothing but gates, IOs, memories if you are having any, and the delay values of that particular cells are getting characterized or getting picked into the tool with the help of algorithm which is already set, that is a delay table. So how they are getting over, as I told you, how they are picking the delay value of that particular cell as the same values, they get to know by doing most of the time simulations. It is an iterative process, obviously. They iterated so many times and come to that particular delay value. So this library might compress over 300 cells. So the next input is the SDC file. So SDC is nothing but Synopsys design constraint. So here in the SDC file, what we do is we set the timing targets that we are constraining in the form of a file called SDC file, where we are giving the performance information where it which frequency it has to analyze. Okay, so these are the list of timing constraints that a particular SDC file will be containing of. So in the complete STA session, like from today on, we'll be discussing in depth about this complete clock definition constraints, timing exceptions, delay constraints, and what are this max tran, max cap, and how we can optimize power area according to our usage, and with the help of SDC file without knowing fixing. So here let us first discuss some timing attributes that are needed to implement the process of static timing analysis. So usually you have checked out this file previously also. It will contain the clock frequency and it will contain the port delay values and port transition and load values. So this is just an example of an SDC file. So what do you get as an output of STA is you get the timing reports and some log files. So timing reports are the reports that you, with respective of what timing you are checking, it might be setup timing or hold timing. And the log files will contain the history of the complete execution process that you have run in the STA environment. Okay. Next is the timing paths under consideration. So, which paths we are going to check? That means the complete design at a time we can't check, right? So, the design is segregated into some timing paths. So, we need to mention in the run.tcl file which paths we are going to check, and it will generate the reports for that particular paths. And if there are any constraints and exceptions that you need to give, that means there will be some timing paths in your design where you should not do timing report analysis for that particular timing path. So that path, that process also you need to give, and that will be also like executed in the report files. As I told you, log files will consider the runtime execution flow. So when you invoke a tool, you would have observed a file called .log gets generated when you invoke a tool. So that log file is containing the complete history of the execution process, whatever you have implemented once you started invoking the tool. So here, why we are doing at this process is it will be easier for us only to send this particular gate level netlist to the physical design process. We are just rechecking it if my timing is better or not. So as you can see, it is not checking any functionality, and we are not giving any vector as an input. So it's a non-vector analysis technique which forms timing paths defined by start points and end points to aid the analysis of timing. So to understand this all timing paths, what is timing, what is cell delay, you need to know some timing terminologies. So what are the timing terminologies? Let us get into the each and every terminology. Now, a design usually contains mostly of sequential cells only. If you would have observed in your gate level netlist that you have generated also, so the clock will be deciding the delay values of the combo logic that is connected to the sequential cells. So we need to know what is clock. So it is only defining our timing, it is only defining our power, and it is only defining our area, obviously. So what is clock is it's an sequence of repetitive pulse which is generated from off chip or external clock oscillator. So what is oscillator is it's a clock generating circuit where your propagation of the clock starts. So why we are using clock? It's basically we are having most of the gates in the gate level netlist, and any circuit that we are going to implement is mostly of the sequential cells itself. So obviously it needs a clock triggering to run the data. That's the reason we are defining clock. So it's the fastest signal in the whole design, and all the synchronous designs need a clock for its operation. Remember this point, we are already discussed regarding this also. We do the static timing analysis process only for the synthesis, I mean to say synchronous design. So functional and other synchronous clocks required by the design are generated internally from PLL, whose reference clock might be the crystal oscillator. So there are two types of clocks. So if your gate level netlist is there in this particular area. Now a clock might be a source which is coming from the outside world, or a clock might be in the form of PLL, which is defined in the form of module in your RTL circuitry or RTL functionality. So there are two types of clocks we usually use in industry. One is PLL, that is, and the other is clock oscillator. So clock oscillator will be usually present outside. And the PLL usual sometimes it might be also inside the module that you have your gate level netlist is comprising of. So whatever frequency or the period, timing period we are giving in the SDC will define the performance of the system. So there are some terms that like you need to know about the clock, because in the later stages while checking the reports you will be coming across this kind of terms. So let us discuss what are those terms. So what are clock edges is the transitions wherever that rising and falling of that particular clock is happening is called a clock edge. So if you can see the clock waveform, here my rising edge is happening. That means transition from 0 to 1 is happening. So this particular edge is called a clock edge, and it is taking a transition from 1 to 0, and it is also another clock edge. So we define this transition states as clock edges. So there is another terminology. One is transition time, or some might call it as slew also. What is transition is the time or the change of the signal that is taking it to drive it from 0 to 1 while it is changing its state. So here you can just see an example. So whatever rate it is changing, like from low to high, this particular change of state is called as transition. And with what percentage it is changing, from 0 to 90, or it might be 20 to 80, something like that, with what rate it is changing, that is termed as slew also sometimes. So there are two types of transitions again. One is the rise transition, the other is fall transition. So when it is changing from 0 to 1, it is called as rise transition, and when it is changing from 1 to 0, it is called as fall transition. So what is delay? This I have discussed in the library thing also, library file description format also. So the delay is nothing but the propagation delay. Once given an input to the gate, how much time it is taking, or how much delay it is taking to give an output, that is termed as cell delay or propagation delay. So there are two types of delays. One is cell delay. So again, cell delay is segregated into three terms: intrinsic delay, cell delay, and the slew or transition time at the output pin of that particular gate. And wire delay is nothing but the net delay. So net delay due to the parasitics. Now, a cell delay is basically dependent upon two parameters, as we discussed before also. It depends upon input transition and output load at the particular gate. Now, this particular output pin will not be floating. It definitely have to get connected to some other gate. So, what should be the transition value at the input pin of that gate? So, that also we need to discuss here, and that also we need to pick it from the library file. So, that's the reason we calculate slew or transition time at the output pin of that particular gate also. Usually, the two terms, that is cell delay and the transition time at the output pins. Now, what is intrinsic delay is, as I told you, cell delay depends upon input transition and output load. Now, if a cell is having zero input transition and zero output load, then also there is some delay that particular cell is getting exhibited. So there is some minimum number of delay a cell will exhibit when it is having a zero input transition and a zero output load value. That particular delay is called as intrinsic delay. So cell delay is the delay when we are giving some input transition and some output load value. Intrinsic delay is with zero input transition and with zero output load. And slew and transition time at the output pin, as I discussed. Wire delay is due to the delay. That means here, if you see, this is my input pin, and from input to this gate, I have some net. So this particular net will also project some delay depending upon the conditions, operating conditions, and the PVT process voltage and temperature models. So that particular delay also we need to take into consideration when you are generating a timing report. Okay, so what is transition and load? The cell delay or the propagation delay, as I discussed. So if you are I mean to say, if your transition at the input pin side is happening in a rise form, or it is the transition is happening in a 0 to 1 change state format. So that particular delay table will be picked, or the delay value will be picked from the cell delay table of rise cell delay. And if the input transition is a change of state from 1 to 0 or the fall transition, then the delay value of that particular cell will be picked from the delay table of cell fall delay. So you might have observed in the library file there are two tables, two delay tables and two transition values for a particular cell. So rise cell delay is one table, fall cell delay is one table, and the rise transition at the output pin and fall transition at the output pin. So cell delay is a function of input transition and output capacitance. So input transition is the time it takes from the input pin to switch between logic states. It might be low to high or it might be high to low. And the output capacitance is the capacitance that needs to be get charged or discharged at the output of that cell driving signal or multiple loads. So you are not sure, right? At this particular output pin, there might be a load, or there might be an interconnectivity of other cells with one respective cell, or there might be multiple loads also, multiple gates also connected at this particular output pin according to the gate level netlist. So that we taking into consideration the capacitance values by summation of this complete load value, the delay value of is picked in the delay table. So intrinsic delay, it is defined as the delay from input to output pin near the zero slew or zero transition at the input, and output pin has no load connected to it. So when a cell is projecting a delay without I mean to say with zero transition and zero load value, that particular delay is called as cell delay. So why this particular intrinsic delay is causing is when a voltage is given to particular cell due to the internal parasitics. That means if I'm giving an inverter while it is going for a manufacturing, take an example of this particular inverter itself. Now every gate will be manufactured or fabricated in the form of CMOS. So this when it is getting fabricated in the form of CMOS, there will be some internal net connections, like from PMOS gate to NMOS gate and NMOS gate to PMOS gate. There will be some internal parasitics present in that particular circuitry. So they have observed that when it is going to that manufacturing process without giving any input, or without giving any input at the output pin, that is input transition and output load, they observed some delay is getting projected for that particular cell. So that particular delay value will be dependent upon the again width of that transistor gate and some internal net connections of that PMOS and NMOS circuit when it is getting fabricated in the CMOS form. So that particular delay value, whatever it is projecting, will be the minimum delay value offered by that particular gate. So net delay is the interconnect delay due to the physical wire. It is called as also wire delay. So to connect from one gate to other gate, it is using some wire. So that particularly is projecting some delay again. That delay is comprised as this wire delay. Okay. Now, you need to know some terminologies called as arcs. So, as I told you, STA is not implemented completely at a time. It is broken into some paths, and for each and every path, there will be some timing parameters that we are going to report. So, timing arc is nothing but for a particular cell, arc, like it might be a delay arc, it might be a constraint arc, or it might be a net delay arc, will be comprised in the library file from where it can pick a timing delay. So if I have a buffer, Now, what it is depending upon, it is depending upon A pin input transition and my Y pin output load. Now, so the timing arc will be, or the delay arc will be from A to Y. So that particular arc which is dependent upon the two sources we are defining, that particular arc is called as cell delay arc. And the net also the same way, if the interconnectivity is there respectively, to which it we are projecting. That means Y pin of that particular buffer to A pin of this particular inverter, we have a net delay arc. So an arc is nothing but where we are projecting the delay value that it has to calculate. That arc, we define it as a delay arc. And there are some constraint arc also. So this comes when you go to a sequential cell. So constraint arc is defined only for the sequential cells, because in the constraint arcs you need to know basically two set of timings again. One is setup timing and the other is hold timing. So we'll check in the later stages, like later slides, I'll just show you what is that constraint arc and all. Now I just took an example of small circuit where you can see the whatever is there in blue color. That means where the cell delay values I need to check, that particular arc is defined in blue color, that is cell delay arc. And net delay arcs are the interconnectivity arcs, and constraint arcs are for the sequential cells which are given in the green color. So why we are checking for a sequential cell from the clock? So the data will be launching or getting captured only with respect to clock. So what do we, the cell delay arc for the sequential cell will be clock to Q. And for I mean to say for the combo logics, it will be just input and output because there is no clock reference coming for that particular gates. But for a sequential cell, because my D input will be getting transferred depending upon my clock input, that's the reason the delay arc for the sequential cell will be from clock to Q. For the combo logic, it is from input to output, but for the sequential cell, there is a change because it is depending upon the clock input. That's why the delay arc will be defined from clock to Q. Now, there is a constraint arc also. There are some timings we check, as sir discussed about the introduction, some hold timing and setup timing for each and every flop. Now, this D data is making changes in the transfer when the clock is getting triggered. So that particular setup timing arcs and hold timing arcs for the sequential cells, we define it as a constraint arc for a sequential cell. So here are the examples, like how the delay arcs for a simple complex gate and a sequential cells will be defined. So if you take an inverter, there are two delay arcs and there are two transition timings. So for every cell, as there are four tables, if you can see in the library, recheck it again. There will be two delay tables and two transition tables for the output pins. So the related pin to get the output Y is the A pin, because at Y it depends upon A input only. So that's the reason the relative pin for a inverter is for a Y pin is an A pin. So usually what are the timing arcs that are there are A to Y cell delay, and that is cell delay might be again a rise cell delay or fall cell delay, and the output transition for rise and fall. So you completely, if you consider a simple not a gate or an inverter, you will have a set of four timing arcs. So in the same way, if you consider a NAND gate, these are the list of arcs that you will be having. So a 2-input NAND gate has 6 timing arcs associated with it. And for the delay arcs of a flip-flop, these are the set of timing arcs and transition arcs that will be there. So As I told you, there are only two arcs for a flip-flop. One is constraint arc, that is cell delay arc, that is clock to Q, and a constraint arc, that is clock to D. But there is no timing arc from D to Q. Without clock triggering, there can't be any change in data, right? That's the reason. There is no arc from D to Q. There is only one arc, clock to Q, and the constraint arc is from clock to D. So let us discuss what are these constraint arcs now. So constraint arcs are associated only with the sequential cells. So it is defined between two input pins, or for an input pin, as I told you, it is defined between two inputs, that is D pin and a CK pin, with the given slew or the transition. So specifies the timing requirement of clock and data pins for the given slew and clock data pins. So here Here you can see a example of flip-flop where cell delay, that means input slew of clock, and output load at Q is defining my cell. But due to the data change or the data whatever I'm giving at the input, it is affecting my clock with respect to some setup and hold. So that particularly is again taken care by the library file itself. Under the sequential cells, you can check it once again. You will have a cell delay table, rise transition and fall transition table, and a setup table and a hold table. So with respect to clock and D pins, there is some table given under for each and every sequential cell, where the setup timing and hold timing of that particular flop will be varying according to the usage it have been proposed in the gate level netlist. So now you can reframe it in such a way that cell delay is dependent upon clock transition and the output load at Q pin, and setup and hold timing is dependent upon the D pin transition and clock pin transition. So the value of setup time and a hold time of a particular flip-flop got varied according to the transitions that are happening at the D pin and the clock pin. That's the reason they have created some lookup tables for the transition values also, and they have reported an a lookup table for the setup and hold timing. So after once the timing arc is done, there is some other timing attributes that you need to know. Okay, what is a timing point is, first let us discuss what is timing point. So node at which the timing data is present. So here if you can see in the below diagram, here the data is present at this particular combo logic circle or anything you can see. Here, my data is stable within this particular D pin. So this point, wherever my data is coming with respect to what circuit, that point is called as a timing point. Now, what is a timing path? There are some paths that you need to analyze. The circuit is broken into some paths, right? So there are some paths according to that where we are consisting the timing analysis. So as I told you, there will be segregated into fewer parts. One is input to register, register to register, and register to output. Usually the start points will be input ports or the clock pins for the register to register part, and the end points will be like the output ports and the Q pins or the data pins of the receiving flops. So this we'll discuss in the later slides. So a timing path is nothing but a path which is holding a delay. So if you consider a timing path from input to register, so this is a valid timing path. For example, So a timing path is set as the input pin is taken, or the start point is taken as an input pin, and the end point is taken as this particular register. So this is how a timing path is defined, and we verify the timing analysis or the setup or hold timing analysis from this input point to the register. Okay, so you can see any circuit, in the gate level netlist form that you get if you are an STA engineer. If complete circuit will be segregated only with the naming attributes of such kind of paths. So those paths are nothing but the circuit will start with an input port and end with a register. That will be one set of paths, and a circuit starting from register and ending with a register will be another set of timing paths, and a circuit which is starting from register and ending with output, that will be another path analysis, and a circuit which is not having any sequential cells in between, and it is only having a combo logic directly connected from input pin to the output pin of the gate level netlist. That particular logic is considered as input to output port. Now the gate level netlist, whatever you're getting, have to be analyzed with this paths itself. So the valid timing paths that a gate level netlist will be segregated is this kind of paths. So register to register, input to register, register to output, and input to output. So these are the four timing paths that we are going to analyze in the later analysis part of this session. So to do the analysis in the static timing analysis tool, as I mentioned, the Tempest tool, we need to give some valid start points and valid end points to implement the timing or to report the timing. So the tool accepts only some set of valid start points and valid end points. So it is segregated in four parts, right? So for an input to register, that means for an input to register, let us suppose this path, the valid start point or the begin point will be the input port. That means you need to mention in the tool like my valid start point is input and my valid end point is D pin. For an input to register path, the valid start points and end points are mentioned as the input port and D pin of a flip-flop 2. And for a register to register path, as I told you, cell delay of this particular register will be dependent upon the clock pin. That's the reason when you consider a register to register path, the valid start points and valid end points will be starting from the clock pin of the launching register and clock pin of the capturing register. So the valid start points are like CK pin, that is the clock pin of this particular register, to the D pin of this particular register. The sequential cell which is attached to that particular launching register, that is nothing but the capturing register. So for a register to register path, these are the valid start points and valid end points. For a register to output, in the same way, it is starting from the clock pin of this because the delay is dependent upon the clock pin, and your output pin will be the end point, valid end point. So if there is a combo logic, as of now there is no combo logic. If you have a circuit as such, as shown in the previous slide, like there is some circuitry without any sequential cell connection, there is only combo logic, and this combo logic is attached to the output pin. In such cases, your reporting analysis in the tool have to be as a valid start point as an input port, and your end point should be the output port of that gate level netlist. I hope it is clear till here. Any queries like regarding timing arcs, timing paths and all, so that I can move on to the next session?
Shravanti, are you considering only block 2? Can we connect a block 1 to block 2?
Okay.
So
So
if you
yeah.
if you if you if you consider block 1 to block 2, maybe register to register, it may be clock 1 and via B1 B2 till D, right?
Okay, wait. So here,
Can we connect like that?
yes, let me complete. So here
Okay.
I have say is if you see the example, I have segregated this complete circuitry in different blocks. So as a block owner or as a design owner, like as a backend engineer, you will be getting the gate level netlist of this particular block to itself. So whatever clock one is with respect to the your friend's block or your communicating block. So it is mandatory that this clock 1 and clock L should be synchronous. But with respect to this clock, you can't connect your own clock. So it is wrong that when you're doing full chip, it might be a register to register path. But when you are a block owner, your block will be starting from the input port itself. Is it clear?
Okay. If you consider a particular block, this is okay. Yeah, we understand.
Yes. So I just took an example of this block 2.
Okay,
And for
okay.
that block 2, I was explaining this valid start points and end points.
Yeah, yeah.
Yeah.
Then it's okay. Yeah.
Yeah.
Thanks.
Okay. More any queries? Or shall we move on?
Hello,
Yes.
ma'am. Those buffers are used, no? B1, B2. What is the functionality of that? Yes, whether that is not counted in path.
It will be contributed in the path. So that analysis we'll be doing it in the later sessions. So, but what are the endpoints and starting point? There are only some when you're considering this input to register, the combo delay is also comprising in it. Definitely, it will also comprise. But tool will
But
accept it as an input to register path when you are mentioning such begin point and end points.
okay, ma'am. Thank you.
Hello, hear me?
Okay.
Can you hear me?
Yeah. Yeah.
Case of register to register in between, suppose if combination circuits exist, then how help?
That delay also will be contributed in the timing part. So let us discuss the next session so that you'll get a clear idea. Like while doing analysis of that, you will have to see. Now, you were mentioning this, right? So you'll understand once the slide is done. So there are two paths, like if you consider a normal register to register path. So register to register path, you have two types. One is data path and one is clock path. Uh, as you guys were addressing, what about this buffer? So that buffer also will be compromised in this particular register to register itself. So the delay value of this buffer and the delay value of this cell will be the complete data path of that circuit of register to register. So what is clock path is the timing path which is starting from clock input port through one or more buffers or inverters to the clock CK pin of the capturing register with some buffer delay. So when you are considering these two paths, the delay also is getting added. So for this, the clock path is the clock propagating path, and the data path is obviously from the CK pin of the sequential cell, because the delay value of that particular cell is depending upon the CK to Q arc, that is the timing arc or the delay arc. The delay value of this, that is clock to Q plus A to Y till D pin. Okay, so these path wherever my data is handling is, or the delay value of that particular cell is getting handled, that path is called a data path.
Which one is the begin point and end point?
Sorry, I didn't get you. Can you be more specific?
In
It
that
is not
case,
audible proper.
this diagram,
Huh?
which one is the begin point, which one is the end point in data path?
CK pin is the starting point, I mean starting point or begin point, and D pin of the capturing register is the end point.
What about the in the delay,
What about?
that buffer delay?
Yes, buffer delay also I'm adding, right? So A to Y delay also is like till the D pin of the capturing register, whatever data is there, how much ever combo logic is there in between, that also will be contributed in the data path. Okay, clock path is the clock propagating path for the sequential cells. For input to output pure combo, there is no involvement of clock. In that case, why should we consider clock frequency calculation? Okay, so here there's a question like for the input to output path, why we need to consider the clock. Here, if you can see, here the circuitry is something like there is some sequential cells in the my present working block. But if the circuitry is same for block 1 and block 3, but from this end to this end, I have only combo logic. So whatever input data reaching at this particular input pin of that combo logic is with respect to the clock of that previous block. So that is the reason we consider the clock parameters for the input and output like input to output blocks or input to output timing paths also. So if the combo logic is also there, the input pin is getting the data from the previous block, which is having a sequential cell. It might have or it might not have. So we need to check the data that is coming at the input pin with respect to the previous block is proper or not. That's the reason we consider the clock for the input to output cells also. Okay, so here there are some terminologies for launch clock and capture clock. So what is launch clock is when you take a register to register path as an example, like your circuit is segregated into a register to register path, whatever clock that is getting triggered at the first flop, that flop is called launch flop, and the clock which is getting triggered at that end is called launch clock for this asynchronous circuits. This is an example for asynchronous and this is an example for synchronous circuits. So launch clocks are the clocks connected to the launching flip-flops, that is F1 and F3 with respect to synchronous and asynchronous design. And capture clocks are the clocks which are connected to FF2, that means the capturing flops or the second connected flops with respect to the launching flops. That clocks are called as capture clocks. Okay. So timing analysis is basically done in 3 types of paths and 2 types of analysis. One is clock paths, data paths, as I mentioned before, and asynchronous paths. So there are some clear reset pins also for the flip-flops in your gate level netlist. So for such kind of paths, we do perform some asynchronous checks also, and that paths like which is not connected to any data pin or any CK pin, and we are just using some reset pins or clear pins for the flip-flops, if you can see here. So this paths also will carry some delay, right? So we need to analyze for that paths also. That paths are called as asynchronous paths, and clock paths are the clock propagating paths, and data paths are the paths that are holding the cell delays. So in the types of analysis, we do perform asynchronous analysis also, remembering the exceptions. So one is synchronous, that is clock to data paths, and Asynchronous is clock to async paths. So one is synchronous is, as I told you, clock to data, that is setup and hold. So clock to darc is the setup and hold arc. And the other thing is clock to clear or clock to reset. So we do perform such kind of analysis also. So how we are going to perform? It has a format that we'll be discussing later. Now, let us again take an example of this particular register to register circuitry itself. So the edge where the data is getting triggered, that means here. So wherever the data is getting triggered, uh, it has to launch the data here. That means the clock is getting triggered here, so the data have to get launched here. That's the reason wherever that particular clock is getting triggered, that edge is called as a launch edge. And now it has to I mean to say, it has to transfer the data till the D pin of the second register within some time period. So that with respect to that particular time period, wherever it is capturing, that means from wherever the next cycle is starting, we don't bother about that. But wherever it is capturing, that means wherever the D pin is getting captured for the following sequential cell, that edge we call it as a latch edge. Now let us suppose a clock is getting triggered here. Now a data is getting transmitted and it is getting captured at this end. So this edge is called as launch edge, and this edge is called as capture edge or latch edge. So the data arrival time we need to calculate, right? So here you can get a clear idea now. See, now once the data or the clock is getting triggered, here the clock is getting triggered. Now my data have to transmit. That means the delay value of this particular register, the delay value of this combo logic have to get captured at this particular CK pin of this register 2. Now if you see the diagrammatic representation, now my clock is getting triggered here, and you need to include the register 1 delay. Yes, so register 1 clock is getting here, and you need to include the combo logic also. So T combo, like TCO, sorry, TCO delay of that particular one register is getting added once after the data is getting triggered. Now, as you guys addressed, the combo logic also will be introduced. Now, at the register 2, it is getting captured at this particular amount of the clock. So here the data is getting launched. It is traveling this much of my clock period, and it is getting captured at this particular register to register cycle. So here, if you can see, my data arrival time will be the summation of the register delay plus the combo delay. Okay. So the launch edge is the edge wherever the data is getting launched, and T clock to TCO is the delay of that particular register, and T combo or the T data is the delay of the combo logic. So yes, the data of that particular combo logic and a register is taken care till the end point, that is the end point of my sequential cell. In the same way, clock also have the arrival times. So if you can see, the register clock might be having some delay. So if you consider same register to register circuit, it is getting triggered at the without any delay. But if it is having a buffer or any some cell in the clock path, a clock buffer or a clock inverter, the triggering of this CK pin will be delayed. So that is what here they have mentioned, that the clock arrival time will be different for the launching registers and the capturing register. So here is the clock waveform. of the launching register and register to clock. If there is any delay, the clock waveform replicates as such, and the clock path arrival time will be the combination of delay of that particular buffer till that particular register. So the clock path is a combination of the delay that is contributing from the clock port with along with the combo logic in the clock port till the clock pin of the register, that is the capturing register. That is what I've mentioned here. So the clock arrival time will be the latch edge plus T clock 2, that is if it is having any delay. Now, so you need to know two things. One is the setup time and hold time. As sir discussed before, setup time is nothing but the time where the data have to be stable before the triggering edge of the clock. And hold time is the time where the data have to be stable once after the triggering edge of the after the triggering of the clock. So they have observed such things like once the data is getting launched, it has to get captured at this particular window. Yes, this is nothing but the latch edge or the capture edge. Now, when it is exactly capturing the data at that particular edge, that means there are some metastability issues arising. That's the reason they take care, like before that register, they make some settling time. That is, if you take this register to clock, they made some settling time as a setup time. If the data is coming in that window, that means it is violating. So before and all, it can launch the data excluding that setup time. If it is coming in that particular window of that particular clock triggering, there are some issues arising as some setup violations and hold violations. That's the reason when they are considering a register to register circuitry, they made some settling time before the triggering of the capturing edge, so that if the data is coming in that particular window, that is not safe for me, it might arise to some violation. So we make sure, as we are analyzing the timing reports, the data must be valid before that setup window itself. If you can see now, the data passing the sequential cell to combo logic, it is getting launched at this point. So here the data is launching before only, right? Because that is the reason the data will be valid. So the data required time that it has to capture should be the complete clock arrival time minus setup time. So the complete clock edge or the clock time period minus setup will be your clock period that a data should achieve. So in the same way, for hold also, the data should be valid once after the triggering edge of the clock. So if the data is getting launched once after the triggering edge of the clock, so if it is launching at this particular window, they observed that there are some violations happening and metastability issues coming into picture. That's the reason a window is created once after the triggering edge of the clock. So if there are launching if the data is launching in that particular window, they will arise to hold violations, and we can make sure to achieve the data before the, I mean to say, before that window or after that window. So the data required time for in the hold case will be clock arrival time plus hold, plus why it is it is happening after the clock edge. That's the reason we are adding it to the clock time period. So slack is the difference between the arrival time and required time, or required time and arrival time, depends upon the slack that you are calculating. So arrival time is the time taken by the data to travel to endpoint, and required time will be the data travel to the endpoint in the clock path. So slack is required time minus arrival time when you are doing a setup analysis. And if this value is a zero value or any, I mean say any positive value, so if this slack value is positive, then we call it as a positive slack, and if it is a negative value, it is called as a negative slack, and if the value of the slack is 0, we call it as 0 slack. Now, when it is positive and when it is 0, we we conclude that the timing requirement is met. That means we can close the timing issues without any violations. And negative slack is nothing but it is having a violation. So if my slack is negative value, that means I need to do some manipulations with respect to my SDC or with respect to the logic that is present in between that path. So negative slack, we need to fix it. Positive and 0 slack is something like we are meeting our timing requirement. So that is what I mentioned here. Positive slack and 0 slack are called as timing met, and negative slack are called as timing violations. So setup slack is the difference between the data arrival time of the data path and clock arrival time of the clock path. So that is what I've represented separately here for a register to register path. Now if you can see here, the data is getting launched here. So at this particular point, now my data have to be stable within this window when I'm doing setup analysis. So whatever window is left out for me, difference between this required time and this is my arrival time of data. So this is my arrival time of data. So my data is getting launched here, and my data is have to be launched before this particular setup window. So this will be my required time and this will be my arrival time. So the difference, whatever the window is there, that window we define it as a setup slack. So setup slack is the data required time and the difference of arrival time. So in the same way, hold should be stable after, right? So the data will be valid only here. So once after the triggering of that, and this will be my hold. My data is getting launched here. So this particular window between my required time and arrival time is hold slack. So hold slack is data arrival time minus data required time. Okay. So there is one topic called as virtual clocks. So when I am doing the timing analysis as a block owner, that means I am doing the timing analysis as a block owner. That is, I am an owner of block 2 where I need to perform timing analysis. Now, what about the input and output port wherever I am calculating timing analysis with respect to what clocks? I need to have an idea while I am performing timing analysis for the block 2. Now, we don't have an idea or specification with what respective frequency they are propagating. That means the side blocks or the communicating blocks of my block, what are the clocks that are propagating to that communicating logics? I don't know. So, in such cases, as a block owner of block 2, I suggest I write a constraint in an SDC file telling that consider a virtual clock. That means this virtual clock will be the source of the inputs and output ports of my block. So it is just a reference clock for my input and output ports. So here the clock 1 is my virtual clock at this particular input port, and clock 2 will be the virtual clock at the output port. So these are just the reference clocks with what it is getting launched till my ports. So that ports or that clocks should be sequential with respect to the clock L and clock C. So clock 1 is the virtual clock at input port and clock 2 is the virtual clock at output port, where I'm assuming the frequency. So why it is done is we can't do the timing analysis for the complete circuitry. So they are divided again into modules, and that segregation of clock logic is again taken care in the design partitioning stage. So whatever input ports and output ports are there for you as a block owner, they are coming as a reference with the previous blocks, previous block clocks. So just we are creating some virtual clocks so that we are in sync with the communicating blocks. Here you can see in block 2, clock 1 must be synchronous with clock L and clock 2, and it has to be synchronous with the communicating block of output pin also, that is clock C. Yes, these are the virtual clock parameters that okay. So more any queries regarding this about virtual clock slack and the data arrival times and clock arrival times? Okay, so there's a query, can we have slack in 1000 seconds? Can you just tell me, like, did you analyze the things in seconds, nanoseconds, or picoseconds so that I can give my answer? Okay, it's in nanoseconds. 1000 nanoseconds, it's a huge margin. So, okay, we can't have that much huge margin of positive slack also. So if it is 1000 picoseconds, then it's 0.1 nanoseconds. It is fine. My positive slack might be that much, but 1000 nanoseconds is a huge margin. So that much positive margin also we should not have as a slack value. Okay, please repeat the setup slack. I'll do that. Before that, there is some question. Chill clock. How to calculate intrinsic delay? So intrinsic delay is calculated by the tool. As a user, you can't do that process. It's an again interpolation process done by many simulations. So the intrinsic delay is again calculated by the tool itself. The tool is automated in such way where when you're not giving any transition and load values, the delay whatever that particular cell is representing is called an intrinsic delay. Okay, so is there any limit that this much slack should be there? Okay, so yes, there is a limit. It depends upon the application of your chip that you are performing timing. So according to the frequency that you have designated and the gate count in your gate level netlist, obviously the margins will be set for your setup slack and hold slack analysis, that if it is meeting this margins, it is fine. Okay, difference between virtual clocks and clock C and clock L. Virtual clock itself is a clock C and clock L. Okay, now let us take this diagram. Now, I have an input port for this block. Think I am working in this circuitry and my output port is out. Now, whatever delay, whatever input delay it is projecting at this particular input pin is with reference with the communicating block. It is not coming just as an input delay from where the block is starting. It will definitely have the reference, which whatever it is projecting at the input delay or the input port delay with respect to the communicating block. Now that communicating block will you are not sure. I mean to say, you're not sure it is having a sequential cell or it is having a combo logic itself. So, as a block owner of this block 2, you will not be knowing that input port which is coming from the other block or the other communicating block is with respect to clock or not. That's the reason we just assume a reference clock. That reference clock for the input ports and output ports, we take it as virtual clocks. Hope it's clear. What happens? Slack is negative. How to rectify? That we'll be doing it in physical design process. There are some techniques like upsizing, downsizing, and all, and VT swapping. So that is taken care by a physical design engineer or a physical verification engineer. If you are an STA engineer, the role that you are performing will be just reporting your timing paths of your gate level netlist. So as I told you, the complete circuitry should be synchronous. That means it has to propagate with respect to only one clock. So we assume the reference clock is also same as the frequency of the block. So then only it will be synchronous, right? That's the reason we give the frequency of the virtual clocks, that is clock 1 and clock 2 also has the same frequency of the block. But as a owner, we know virtual clock frequency, yes, it will be obviously same to the frequency of the block, whatever you are operating. Okay, difference between slack and slew. Slack is the difference between arrival time and required time, or the required time and arrival time. But slew is the input transition, whatever you're giving. Transition is nothing but a change of state, right? So that value, whatever you are giving at the input pin of the gate, is called as input transition or slew. Slack is the difference between the data arrival times in the clock path and the data path. So when you check it in the tool, you will be having this clear idea what is slack and all. Okay. More any queries? So as a STA engineer, you need to do two types of timing analysis. One is setup timing analysis, that is setup slack analysis and whole slack analysis. So for each and every timing paths, as I mentioned before, also there will be four types of timing paths that your gate level netlist will be segregated. One is input to register, register to register, register to output, and input to output. For this four timing paths, how we need to analyze setup time or setup slack, or how we need to analyze whole slack, that and all we'll be performing analysis in the later sessions, like how to calculate it manually and how to relate it with the tool automation technique, that is the Tempest tool of the Cadence, how to do check manually and how to relate it with the tool process, that and all we need to do in the analysis part of timing reports. I hope it is clear. More any queries I'll address, or else we'll close the session. Okay. Okay. Let me take a clock signal.
So Shravanti,
Yes.
put that setup Slack slide.
Okay.
Okay, so just to add on, if you look at one of the basic thing what I told about the timing introduction class, it is about the maximum frequency with which the circuit can work. If you look at whatever is highlighted in this green, the setup slack, right? The setup slack, if you look at with respect to the rising edge of the next clock, right? So now you have so much, you have the luxury of, right? It is some extra. See, the minimum setup required is one thing, and this is additional time what you have, right? Similarly, let us say setup time required is 2 nanosecond, and if you have setup time as 4 nanosecond, right? So the additional whatever is it is there, right? That is the window, another 2 nanosecond luxury you have. For example, now you are expecting to reach the airport at 10 o'clock, right? And keeping 2 hours, 2 hours minimum for checking in, right? Check-in time, 2 hours minimum required. You have to reach before, 2 hours. You have flight at 12 o'clock. You have to be there at 10 o'clock. Let us say you are reaching there at 9 o'clock. Now, that 9 o'clock to 10 o'clock is this additional buffer time you have, right? Otherwise, minimum what was expected from the airlines was 2 hours, but you are there 3 hours before. That is what is the slack for the setup. Similarly, right? So the hold part, the this is for the setup, the required, and if same context if you apply for the hold, now you have reached there, right? After reaching, right? So let us say now minimum time expected is 1 hour. Now you are there for 2 hours. Maybe it could be taken in the other context. Maybe flight got delayed, like another 1 hour before, 1 hour extra you have the whole time. So like that, right? The slack is the additional than what is required. Means what? If you look at from the hardware context, you you see here the combo logic, for example. Now the combo logic is the one which is, right, which can govern the those delays. Okay, for example, now the here, if you look at the combo logic, if you have more circuitry here, right? So that means this is going to be increasing. Right now you already have the T data you have considered here. Let us say T data can be extended up till here. What it means, you can, let us say this is taking 2 nanosecond. Now this is 2 nanosecond right now T data. Another, let us say from here to here the slack is another 2 nanosecond. You can add some additional AND gate OR gate logic. You have more room to add the logic in between the flops. So that is what, that is why Shravanti was concluding that positive slack is always good. The moment it crosses this, let us say this one, like I told you the 2 hours before, now the airlines may directly tell, no, 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 you are late, sir. Already, check-in counters, we are closing, right? Then what it means is what is that? Your passenger means the data. Now the data, you say, no, you wait for next flight. I am not going to send you because you are late. So that is, but at the same time, they can apply a discretion saying that, okay, come, you can still, I will give a chance for you, right? So, but it is not predictable. It is not predictable, but they may allow you. So this window, As long as you maintain the setup window, you are safe to get into the flight. Otherwise, you are not sure. So that is what is metastability. It is output is unpredictable. Okay. So now always make sure this here it is setup slack and it should be positive. This is the thing. And go to hold similarly, right? You can go to hold, Shanti.
Yes.
Same. There also you have positive hold, right? So that is good. For example, now after the data here, after the data, you have more time. Minimum required is this much time, but you are holding the data beyond what is required, means you have more room there, right? So that's how you can understand these concepts actually, the setup and hold slack. So it means that you have more time there. See, that's what now setup time, hold time, violation, like Shravanti was telling. Say there are some ways how you can fix these violations, right? That will be the maybe the last session in the STA. We will discuss about it. Right now, let us understand the concept and the required timings, and we'll understand each of these timing parameters and the terminologies, and then how it is, how it works. Now, the next step is feeding this into the tool. Okay, all these design constraints and the timings and input delays, output delays, all this what you are learning, we will feed into the Tempest tool and take a design and then apply and then see the reports, analyze the reports. Then when you are seeing the warnings and the errors and the violations, now what we can do is we will see as a last.
Okay. Now there's a question like if we are having a violations in pre-layout STA analysis, like what we do. So a margin will be set according to your frequency, as I told you. If it is having okay, now if I have complete paths in my circuit as some 200 to 300 paths. Now out of them, if 50 to 40 paths are failing, let us think in the pre-layout stage, my 40 to 50 parts are failing. Now you will get to know as an experience itself this also, like in the later stages this can be getting optimized, but out of 300 parts, if your complete 240 parts or 250 parts are getting violated, so it is difficult in the later stages to optimize that huge number of timing parts. So that analysis again you'll be getting by an experience only while doing the iterative process. So in the pre-layout stage, yes, you will be having some margin to move forward to the physical design.
So, okay, we'll end the session. So, you try out with the steps what Shravanti has explained, the synthesis, one physical synthesis and the logical synthesis. And next session, we will get into the Tempest tool. A few more concepts are there. Shravanti will walk through those concepts and then we will write, we'll give inputs to the STA tool and then we will do the STA part for the design.
Hello, sir. Hello, sir.
Yeah.
Sir, if we have the point of contact during our sessions, that will be useful for us, because if we have any queries, any doubts, if you send the mail, whatever the mail you have mentioned, you are not getting the responses in time. So by the time our session is being over, because since we are new to the tool, we are getting stuck up and our time is not being utilized properly. One point of contact is there during our sessions, that will be better, what I feel.
Every session, somebody, now Saraswati was there from the tools team today also. People are attending actually every session. Saraswati are still there. Now, only thing, I don't know the name. Is it Manjula?
Radhika.
Radhika. Okay. So now what?
Yes, sir, I'm there.
Okay. See, there is a team to support because we are having more users. there is a team to support. That's where we are requesting the questions to be sent to the Cadence support, right? And then they are being addressed. So Saraswati, you can comment on it actually. So we'll
Yeah, sir. So if they are facing any difficulties, directly they can contact us, or through mail also they can contact. If any physical, technical related issues or tool related issues, directly you can send us to, or else you can mention what are the problems you are facing and send directly with the mail. Or else you will get our contact details. So through phone also you can contact us.
no, Saraswati, that Cadence support is the mail, right? Cadence support
Yes,
at ntipal.com. So that's first thing. Shravan, so Saraswati, are all these mails are being checked and then responded? Is that happening process wise, or or is it that you are getting too many mails and then you are not or some are getting missed? How that process is taken care?
Sir, actually, they will forward a mail to us. After that, we are taking and putting into the tickets. Then we were replying to the customer. Sometimes what happens, they might be starting on these tools practice with the allotted slotting time. So sometimes they might not get a reply at that time.
See,
So
yeah. So I think that is.
Yeah, that is the problem. During our session, we are not getting the reply. Means our session will be elapsed, no, madam.
Ma'am, actually you can contact us. I think whatever the manual starting we have provided, in that we have already mentioned the contact details of our team members, technical team members.
No, Saraswati, you can even you can mention in the chat window what number they can call.
Yes.
So let them reach out and let us respond promptly.